Welcome, everyone. My name is Glenn Starkman. I'm professor of physics here at Case Western Reserve University and director of the Institute for the Science of Origins, a partnership of Case Western, the Museum of Natural History, and IdeaStream. Tonight, welcome to the Origins Science Scholars Program and our third lecture in the series about cosmology entitled In the Beginning. The first lecture, I hope you'll recall, was on the case for the Big Bang, in particular the size of the universe, the fact that the universe is very, very big. And it's getting bigger, and because the fact that it's getting bigger means that it's cooling, and so was once much hotter, which is very fortunate for us because it means that it glows. We can see the glow of that much hotter time back when the universe was a mere 400,000 years old. So over 13.5 billion years ago, the universe was much, much hotter, the same temperature as the surface of the sun. And we can see the light coming from that time right now. We call it the cosmic microwave background. Microwave because the light has been stretched so that it is now, instead of being visible light, is long wavelength light called microwaves. And we talked some about that. Last week, Dr. Gates talked about dark matter and dark energy, the case for them, what they are, or what dark matter might be, what dark energy might be. And tonight, I'd like to talk to you about the very earliest parts of time in the universe, in the beginning. So first, I'd like to talk about how the universe got so big. And we'll find that that process, while very effective at making the universe big, is also very effective at making it empty. And so we'll have to ask, where did all the matter come from? Where did the stuff that we are made of come from? And in particular, we'll talk a little bit about some of the lightest elements and where they came from. So let me remind you about this picture that I showed a couple of weeks ago. Here is a picture of us at the center of the universe. We know that we're not really at the center, but from our point of view, looking out, we see the universe around us. And as we look further and further out, we see the solar system. We see out beyond the planets, we start to see stars, and eventually we get out through our galaxy, out to further and further galaxies, out to the very largest structures in the universe, clusters and superclusters of galaxies. And finally, we're able to look out to this microwave background radiation, which is coming from seems to be coming from a sphere centered on us. It's not that we're at any special place in the universe. Anyone sitting anywhere in the universe, we believe, would see exactly the same thing. Not precisely, but nearly the same thing. It's just that the light has been traveling to us since a particular moment, since the universe became transparent when it was about 380,000 years old. And what we see is actually remarkable. This is a map of the microwave background. It doesn't look very interesting, and that is what is so remarkable about it. Why is it remarkable? First of all, I can tell you that it represents radiation from something whose temperature is about 3 degrees above absolute zero, so very cold. And the temperature of that radiation is almost precisely the same in every direction that we look on the sky. So if you point a microwave antenna in that direction, you'll get radiation that looks like it is from something glowing at about 3 degrees. If you point a microwave antenna in this direction, you'll also get radiation that looks like it's coming from something glowing at 3 degrees. No matter what direction you point your antenna, it looks precisely the same. And that's a big mystery. So here's a picture of that. We can imagine the radiation coming from that sphere that is 13.7 billion light years away from us, traveling to us from all these different directions. And it starts out very hot, blue, and it arrives to us very red, microwaves. But it arrives to us and it has precisely the same energy. Now, to understand why that is so strange, I'd like us to do a little experiment. It's very simple. We're going to count to 10 together and then clap. Okay, ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that was very simple. Doesn't seem very particularly interesting. But now we're going to do it again, and this time I want you to count to yourself, and when you're done counting, then clap. Ready? Go. Now, you'll notice that there was a dramatic difference between those two realizations of that experiment, the two times we ran that experiment. What was different? Well, the first time we did it, we synchronized ourselves. We had arranged to count together, and then when we clapped, we all clapped pretty much at the same time. And when we did it the second time, we didn't exchange any information about how fast to clap or when to start, and so we all ended up clapping at kind of random times. Well, look at the light coming from this distant place. It's traveling through the universe since the universe was very, very young, just 400,000 years old, for the last 13.7 billion years. And it's arriving here on Earth today. And then there's the radiation coming from the other side of the universe, the other side of the sphere, and it too is arriving here just today. And so this place over here somehow knew to send out radiation that would be exactly the same temperature as this place over here knew to send out, so that when they got here, they would be exactly the same, even though there is no way for this point and this point to have ever exchanged a message, because messages can only travel at the speed of light. So how did these two places manage to get to be the same temperature? It would be as if I asked you all to bring in a glass of water, and then when we stuck a thermometer in the glass of water, even though you had all brought them from home where it's different temperature, maybe someone brought it from the refrigerator, someone had it sitting out on their counter, you all brought it in, and we all found that the temperature of the water was exactly the same. Only in this case, the temperature of the universe is the same to just a few millionths of a degree in every direction. To give you an analogy of exactly how smooth that is, it would be as if the difference between the Earth's tallest mountain and its deepest ocean was just 400 feet, shorter than the Terminal Tower downtown. And so our big mystery is, why was the temperature almost exactly the same everywhere in the universe when it was 380,000 years old, even though those places appear, as far as we can tell, to be far too far apart for them to have ever communicated with each other, to have ever come to the same temperature by any kind of process that we can understand. That is really one of the biggest mysteries in cosmology. And we have a story. This is our best story, the only story we know how to tell that explains this. Once upon a time, good stories always start that way. Once upon a time, the visible universe was much, much smaller. And then somehow, the universe got homogenized. Homogenized means something made it get pretty smooth on its own. And then somehow, the universe expanded exponentially fast. In other words, it was expanding slowly, but something in the universe started to drive that expansion faster and faster and faster. And when that happened, places that used to be nearby each other moved apart faster and faster, so that they were moving apart faster than the speed of light. Now, I know everyone thinks that you can't move faster than the speed of light. That's not true. You just can't be seen moving faster than the speed of light. And so it's all right for two people to move away from each other, or two places to move apart from each other faster than the speed of light, because as they're doing that, they can't see each other. The light that one emits will not get to the other if they're moving apart faster than the speed of light. During this process of expanding, remember when things expand, they get colder. And so the universe got very cold and also very empty, because whatever stuff was inside the universe, when we stretched it out so big, it was diluted so that there was hardly any, in any given volume, there was hardly any left. And eventually this stopped, and the universe was filled with an almost smooth, almost homogeneous matter, and normal expansion resumed. And this story we call inflation. Okay, so let's review the story. We start off with this small universe, maybe smaller than the head of a pin. Okay? And that region is small enough that it can come to thermal equilibrium. It can achieve one constant temperature. And then we have to have something that makes that region, which is expanding relatively slowly, expand faster and faster and faster. So the question is, what could cause this exponential growth? Well, it could be ordinary matter, this stuff. The only problem is that this stuff, the stuff that we're made of, the stuff that stars are made of, exerts attractive gravity. It pulls, all the different stars pull on each other. Matter attracts matter through gravity, and that will not speed up the expansion. It will cause the expansion to slow down. Well, so it's not ordinary matter. Maybe it's dark matter. Dark matter is no better. It does exactly the same thing. In fact, that's the reason we think there's dark matter, is because we need something in galaxies and in clusters of galaxies to hold them together, to attract each other so that the galaxies and clusters won't fall apart. In fact, our best guess at what could cause this growth is nothing, with a capital N. So nothing, by which I mean empty space, is very different than ordinary matter. And let me illustrate that with the following example. Suppose I had a box with 12 apples, a nice small box. But the box was made of rubber, so I could take this box and I could stretch it so that it was a lot bigger. Guess how many apples will now be in the box? 12, right? I didn't take any out. I didn't put any in. By stretching the box, I don't generate any apples. So when I take a box of ordinary matter, or a region of space containing ordinary matter, and I stretch it so that it has a larger volume, the density of stuff in the box gets smaller. That's what's happening right now in our universe. The universe is expanding. It's full of ordinary matter. We see, like stars and galaxies. And as the universe expands, the galaxies get farther apart, so the density of galaxies is declining. What about a box full of nothing? So here I have a box, and it's full of nothing. That same box, I took all the apples out, and now there's nothing in it. And notice that if I stretch the box, I still get nothing. Right? But nothing is a very special thing. We think of nothing as not having any properties to it, not having any value. Really, what we should realize is that that box, small box that had nothing in it, when I stretch the box, now has a lot more nothing in it. Okay. So nothing isn't like apples. If I stretch space, I have a lot more space inside there. And so if that space is different than our usual conception of space, then that means I'm actually generating more space. So here is our standard picture of nothing. Right? We think of nothing as nothing. There's nothing there, right? I took everything off this screen, and I don't see anything. This is actually a much better picture of nothing. You see that I've taken everything that we usually think of as information out of that screen, but nevertheless, there are all these kind of fluctuations there, these black and white spots. There's no clear pattern or anything, but something's going on there. Actually, a better picture of nothing would be something more like this, where particles are coming in and out of existence and kind of flickering around and disappearing and appearing and doing all sorts of stuff like that. That would be a better picture of nothing, because if we take a region of space, like a box, and really pull everything we can out of it, we pull the apples out, and then we pull the air molecules out, and we make sure that there's no light inside the box, then what will be in the box is the vacuum of space, but that vacuum of space still has lots of things going on in it. What's going on in it is that particles are appearing for very brief periods of time and then disappearing. Now you might say, well, that means you're violating the conservation of energy. This is another one of those things that people are told, you can't create energy or destroy energy. And that's not true. You just can't get caught doing it. So you're allowed to do it. You're allowed to borrow a little bit of energy from nothing, create some particles, as long as you return them before you get caught. But that process of creating particles and having them appear and disappear filling the space with all these particles actually should have an enormous amount of energy associated with it. And the biggest mystery in fundamental physics right now is not why does nothing have energy, but why does nothing have almost no energy? In fact, there should be so much energy in the vacuum that the universe should be a very hard place to live in. Instead, somehow, almost all of the energy is gone. So, when we have nothing, and our space is filled with nothing, then if we grow the space, we get more nothing, more vacuum. Well, this is a feedback process. It's a runaway feedback. We have the nothing driving the growth. We grow. We have more nothing. That drives more growth, which gives us more nothing. So this compound growth is called inflation. Okay? So we start with a small box, and the nothing makes the box, which is space, grow bigger and bigger and bigger. Here is a picture of a representation of the universe as it's growing. We're meant to be sitting off at this end, looking back out at the universe with our satellites like the Wilkinson microwave anisotropy probe, which looks at the microwave background. And the universe here is growing slowly. We can see an accelerated expansion these days caused by dark energy, but in the past, the universe was growing at a ever slower rate. But back at the very earliest time in the universe, we think that the universe grew explosively, incredibly fast. Let me zoom in on that expansion. So it started from something. We don't know how the universe expanded. People talk about a quantum fluctuation or a tunneling event. The truth is we don't really know how the universe started, although it's very nice to write books that people read about this process. Okay? But right after that, we believe that the universe had this exponential expansion called inflation. And then after a while, it settled down and started to grow normally. So in fact, when we talk about the beginning of time, what we really mean is from the moment that inflation ended. That's when we actually, when we reset our clocks to zero and talk about the age of the universe as starting from that moment. Okay. So approximately, the universe doubles in size in about 10 to the minus 37 seconds. That's a tenth of a billionth of a billionth of a billionth of a billionth of a second. That's a very, very short time. And it keeps on doubling over and over again, so that it grows by a factor of at least 1 with 22 zeros after it. At least that much. Maybe a lot more. Okay? But we know that it appears to have grown by at least that much. Okay? Now, in doing so, remember we started with a universe that was full of stuff. Okay? Then it became that the most important stuff was nothing, was what we call the vacuum. And it was the energy of the vacuum that drove this doubling and doubling and doubling, this growth in size. But now the universe has grown enormously, and there's hardly anything in it except nothing. Well, that's okay for driving the growth of the universe, but it's not very good for building things like stars and planets and people. We're not made out of nothing. We're made out of protons and neutrons and electrons. We're made out of matter. Okay. So the question is, how do you change the vacuum into, well, galaxies and planetary systems and planets like the Earth? Okay. And there's really two things that are missing from the universe at that moment. One of those things is matter. Okay? So as I said, the universe is full of nothing, and what we really want it to be full of is matter. Okay? And we have to figure out some way that we can get the universe to be full of matter. So it's full of vacuum, and it needs to be full of matter. And the second thing is that it needs to be full of inhomogeneities. What does that mean? It needs to not be smooth. Because when we look at the universe, if we go back and look at our picture here of the universe, if we look at our picture of the universe has galaxies in it, it has clusters of galaxies. This does not look very smooth. So we have this period that takes the universe, which is all full of stuff, and stretches it so that it's enormous and very smooth and very empty, and that's great, but it's nothing like what the universe looks like. So we need some way to fill the universe with stuff, and then to make sure that that stuff is not smooth, that it's inhomogeneous. Now, what is the most remarkable part of the story of inflation is actually not so much that it succeeds in making the universe smooth, or that it succeeds in making the universe big, or that it succeeds in allowing the universe to get very old. All of those are important. If inflation hadn't happened, the universe by now should have either been completely empty of stuff, or it should have stopped expanding and contracted and collapsed. So we probably owe our existence in a universe where things can live for billions of years to the fact that inflation did such a good job at making the universe very, very nearly smooth. But inflation also manages to make the universe bumpy. And the reason is that this vacuum that we see here, this picture here where things are coming in and out of existence, which I told you is a better picture of nothing, is grainy. It's bumpy. So in other words, if I took a box filled with nothing and I watched this box, what I would find is that the energy would get a little bit, there'd be a little bit more energy in one corner, and then that energy would disappear. And then if I looked at some other corner, for a moment there'd be a little bit more energy in that corner, and then that would disappear. And this would be going on in the box all the time. Okay? Now, suppose I take this box, and while it's doing that, I stretch the box. Then it turns out I can kind of freeze in this bumpiness. By expanding the box, I prevent the bumpiness from going away. Okay? Now, so we start with this universe which is like a rolling, boiling pot of vacuum. And we stretch it, and we turn those rolling boils, we freeze them. We literally freeze them, and they get stuck so that they can't disappear.
Why does that happen?
Let me answer the questions at the end. But I'm happy to do that. So they freeze into place where they are. And then when inflation is over, and I haven't told you how inflation ends yet, when inflation is over, they're sitting there. And that's really good because those are the things that turn into you. Well, not directly into you. They turn into galaxies and clusters of galaxies. So we believe that we are the products of these things called quantum fluctuations. So quantum mechanics, which in our everyday life is something that governs the laws of very, very small things. We use quantum mechanics to produce lasers. We use quantum mechanics to understand how computer chips work properly. We use quantum mechanics for really very, very small things. But in the universe, those very, very small things got blown up so that they were very, very big, so that they were the size of galaxies and clusters of galaxies. So these very large things, those are the hot and cold spots that we saw in the microwave background radiation. So let me bring up this picture again. So here's a map presented a little bit differently than we saw it last time. You'll remember last time we saw a map of hot and cold spots in the microwave background radiation. What those are is the imprints of these quantum fluctuations that have been blown up from being absolutely tiny, microscopic, until they are the size of galaxies and clusters of galaxies. So we are the results of quantum fluctuations. Now, what happened to those quantum fluctuations afterwards? Well, slowly stuff fell onto them, because where there was a little bit more energy, there is now a little bit more gravity. And where there's a little bit more gravity, that attracted other stuff from around it. So if this was right here, I've circled some of the spots in this map that are a little bit darker. If that was a little bit more energy, then things would start falling in from around it, and slowly this this would get bigger and bigger and bigger. And that process took hundreds of millions to billions of years for those very small quantum fluctuations to turn into galaxies. Okay. Now, I still haven't told you, I've told you that the universe is bumpy, but what I haven't told you is how inflation ends. You can kind of think of inflation, and this is just an analogy, as the universe getting stuck on top of a hill. Okay? What does that mean? Well, the universe is full of all sorts of things that we call fields. What is that? What's a field? Well, you've heard of the electric field or the magnetic field. So if you ever get a MRI, you'll go into a big machine that has a very large magnetic field. Okay? That magnetic field is something that pervades the space inside the MRI, and it carries a lot of energy. There are all sorts of fields that pervade the universe. In order to drive inflation, we imagine that there's a field. We haven't found it yet, but we can write down a theory of such a field. We give it the name the inflaton, which just means the field that's going to drive inflation. And the reason that field drives inflation is the field kind of gets stuck. It would like to be in its lowest possible energy state. So all things tend to lowest energy. But the inflaton gets stuck at a higher energy state than it would like to be. Okay? You can kind of imagine it sitting on top of a hill, and it would like to roll down, but nothing's pushed it over the hill. Maybe there's a little dip on top of the hill, so it's kind of stuck there. And so as it's stuck there, its energy is the energy of the vacuum. Its energy is pervading all of space, driving this expansion, and it can't go anywhere. But all of a sudden, at some point, it fell off. And that falling off is a quantum mechanical process. It actually didn't fall off the hill. It actually probably started on top of the hill, or just in this dip in the hill, and then all of a sudden appeared somewhere else. That's one of the very strange things about quantum mechanics. Quantum mechanics allows objects to move from one place to another without going anywhere in between them. Okay? And in the same way, this field, the inflaton, can start at the top of this, sitting there on the top of this hill and in some, very comfortable in some dip, and then all of a sudden it falls through the hill and ends up at the bottom. And when it does that, it releases all of its energy. Okay? So all of the energy that was stored up in the vacuum, in the inflaton, turns into other stuff. It turns into light. It turns into electrons. It turns into protons. It turns into dark matter particles. So you can imagine this box all full of vacuum, and then all of a sudden, it's full of apples. Okay. What those apples really are the protons and neutrons, really the quarks and the electrons, all the fundamental particles in the universe. The problem is that that's not enough. Just to be full of stuff isn't good enough, because what it will tend to be is full of this exact same amount of matter and antimatter. So what are matter and antimatter? Well, we have ordinary particles called protons and neutrons and electrons. That's what all the stuff in this room is made of, those three particles. But at our accelerators, we can produce a particle that looks almost exactly like the proton. The only difference is that it has the opposite charge. A proton has a charge of +1, and the antiproton has a charge of -1. And if you bring an antiproton, called a p-bar, together with the proton, they disappear. They come together and they produce just light. They produce radiation. And we're not made of that. So we need somehow to get not the same number of particles as antiparticles, but a different number. So, because if we had the same number of protons and antiprotons and neutrons and antineutrons, then what would happen is that they'd find each other, and in the end we'd be left once again with nothing. Where by nothing I actually mean just light. The universe would be full of light. And it's very hard to make things just out of light. What we'd like is something that looks almost the same. You probably can't tell the difference between this picture and this picture, but if I let this picture run, you'll see that there is a very small extra number of protons and neutrons than antiprotons and antineutrons. Okay? So somehow we have to arrange for when the inflaton, when the vacuum decays into stuff, or sometime after that, that we produce more protons and neutrons than antiprotons and antineutrons. This is very hard. A very famous Russian physicist named Andrei Sakharov, who is famous both for being the father of the Russian hydrogen bomb and for being one of the leading dissidents in the 1980s, 70s, and 80s, wrote down the 4 things that we need in order to get matter instead of antimatter. And these are all four of them at the time were things that we didn't think we could have. We now know that we have all of them, and I'll talk about each of them in turn. So the first thing is we need something called baryon number violation. What does that mean? The universe is full of protons and neutrons, and nothing that we could do in this room could change the number of protons minus the number of antiprotons. So we can make antiprotons, but for every antiproton we make, we'll make a proton as well, or we'll make a neutron. If we take all of the protons and neutrons on Earth and count up that number, we are powerless to change that number. Okay? We know no way to do that. The number of protons plus the number of neutrons minus the number of antiprotons minus the number of antineutrons is called the baryon number of the universe. Okay? And we don't know of any process that we can use. I'll talk about some fact that we don't know of any process that we can use that will do that. I'll tell you in a minute about a process that does do it, but we are powerless at this point to use that process. It's possible that process happened in the early universe. That's the first thing. So let me tell you about that process now. So what we'd like to do, and what we look for, we do all sorts of experiments looking for processes that change the number of baryons in the universe. So for example, we take large tanks of water. Water is full of protons and neutrons. And we wait and see if the protons and neutrons could decay. So for example, a proton could decay into something called a positron. A positron is the antiparticle of an electron. So a proton could decay to a positron and a photon, a particle of light. And so we take these very large vats of water, we build very sensitive instruments around it, almost like telescopes, looking at the water, and we wait. And what we've shown is that a proton can sit there for more than 10 to the 32 years, I think is the number. 10 to the 30-something years. Much longer than the age of the universe before it will ever decay. Protons do not seem to decay. What we do know is that there is a process that we've never measured, but that our theory predicts, in which we can take 3 protons, actually not protons, 1 proton, 1 excited proton, and 1 doubly excited proton. So specially prepared things that are like protons. We can smash them together and turn them into a positron, this antiparticle of the electron, plus the antiparticle of the muon. The muon is a particle like an excited electron. And the antiparticle of the tau, which is an even more excited electron, plus some photons. This process is so rare that it probably hasn't happened in the history of the universe since the universe was a second old. It probably has happened nowhere in the visible universe. That's how rare it is. And we know how we could make it happen, but we have no machines that are powerful enough to create the conditions in which it would happen. We would have to create a region that is like the universe was when it was about a billionth of a second old. Okay. So that process can change the number of baryons. Here's something slightly easier. We have to be able to ruin something called parody. Parody just says that the universe can't tell the difference between left-handed things and right-handed things. Okay. Now, so what does that mean? It means that if I'm watching people play, if I'm watching a movie of people playing pool, for example, playing billiards, I can't tell if that movie was taken by the camera looking at the pool table or if it was taken by the camera looking at a mirror reflecting the pool table. There's no way that I could tell the difference between those two things. Okay? And nature, we thought for a long time, was like that. We thought that there was no way we could tell the difference between left-handed things and right-handed things from a fundamental point of view. That particles behave, right-handed particles behave just like left-handed particles. I know you're saying, what's a right-handed particle? Particles don't have hands. Particles don't have hands, but they do spin. Okay? They have a property called spin. And if a particle is spinning in the same way, in a direction so that it looks clockwise from the direction it's moving, that's called right-handed. And if it looks anti-clockwise, it's called left-handed. And it turns out that you can't tell the difference of a movie for when particles are interacting by most interactions. The interactions don't care whether they're right-handed or left-handed. But it does turn out that there's one force, the weak force, that only affects left-handed particles. It doesn't affect right-handed particles, and it affects left-handed right-handed antimatter particles, and not left-handed ones. And that was discovered by Madame Wu, a very famous physicist at Columbia University in 1957, who should have won the Nobel Prize, but back then they didn't like to give it to women. So you can tell whether something's being watched in the mirror, but it's very, very difficult. It's even more difficult if you not only look in the mirror, but change the signs, the charges of all the particles, change the sign of the particles. Okay? So for a long time, we didn't think that there was anything that was able to distinguish that if you looked in a mirror and flipped the sign of things, that things looked exactly the same. And in 1964, Fitch and Cronin showed that that wasn't true. That again, the weak interactions can differentiate between particles and antiparticles, because this process changes particles into antiparticles. So particles and antiparticles we thought were virtually the same, that they had all the same properties except that their charges were flipped. And it turns out not to quite be the same. But it is incredibly difficult to make these measurements to see. You have to build huge accelerators. So this violation is there in nature, but it's weak. The last condition, he said, and this is much easier, is we have to change the properties of the system suddenly. In other words, we have to take it out of thermal equilibrium. How do we take a system out of thermal equilibrium? You do it all the time. You take a pot of water and it has some temperature. Right? And you stick it on the stove and turn on the stove. And now you have a hot place next to a cold place. And that means the cold place, the water starts to change. That's taking the water out of thermal equilibrium. So if we all of a sudden dump some heat into the universe, that would take it out of thermal equilibrium. And there are processes that take the universe out of thermal equilibrium. But the problem is that all of these things are known to happen, but not enough to give us the observed excess of matter over antimatter. So our standard model of particle physics that works incredibly well to explain everything we see around us, from how our computer chips work to how the most exotic particles that we found interact with each other, cannot yet explain why there is more matter in the universe than antimatter. So that's an open question. That's a mystery. Okay. Well, but let's imagine that something happened in the universe. We have some hope that there are processes that when the universe was a billionth of a second old or a little bit less, managed to make matter. We know that happened somehow because we're here, and we know that none of the distant galaxies out there are made of antimatter. At least we know that we have to go at least 5 billion light years away before any of the galaxies could be made of antimatter instead of matter. Okay? So apparently the universe is full of matter and almost empty of antimatter. So we think, therefore, that the whole universe that we see is probably full of matter and empty and not much antimatter. But that still doesn't, that's a universe full of protons and neutrons. How did we make things like carbon and nitrogen and oxygen? Well, it started when the universe was about a second old. And at that time, its temperature was about 10 billion degrees. By contrast, the temperature at the center of the sun is a few million degrees. Okay? So this is 1,000 or thousands of times hotter than the center of the sun. Okay? In fact, it's hotter than the center of a supernova. Okay? So the universe, nowhere in the universe is this hot anymore as far as we know. Okay? And at that time, the universe was full of ordinary particles, neutrons, protons, and electrons, and some other particles called neutrinos that we haven't talked much about, and also photons, particles of light. And what happened is that the neutrons and protons were sitting around, and they would try to get together to form deuterium atoms, deuterium nuclei. So there's a deuterium nucleus. But what would happen is that there were all these very high energy photons running around, and some of them would miss the deuterium, but eventually one of them would smash into the deuterium and break it apart. Inevitably, they would smash in and break it apart. Okay. Oops. And that's what went on for the first 3 minutes. For the first 3 minutes, we had no way to take our protons and neutrons and build them into anything that was more complicated than protons and neutrons, which means all we had was hydrogen and neutrons. And the universe would have been very boring if that continued to be the case, because we would have had a very hard time forming stars or anything else that was of much interest. Then the universe got a little older and a little cooler. And now when the deuterium molecule nuclei were sitting there, what would happen is, let's try this again, that they would come together, they would form the deuterium, and now the particles of light were much rarer. They also weren't quite as energetic. And eventually, another neutron would join the deuterium and make helium-3. And that happened when the universe was about three minutes old. Once that happened, so we go from this period where you're making deuterium, but it's being blasted apart, to this period where all of a sudden we're able to make something just a little bit more complicated, some helium, okay, by adding a proton to the deuterium. Okay? Actually, what happens is a neutron comes in. If we look at this more carefully, watch this. If you watch, you'll see when they come together, and when a neutron zooms in to the deuterium, here it comes, that was actually a proton coming in, a particle of light going out. The other thing that could happen is a neutron could come in, and an anti-electron could come flying out. So that was the first 3 minutes. And then slowly what happened is that we started to get some more complicated atoms. So a neutron could come in and join the helium-3 and make helium-4. And then eventually the helium-4s could come together, and they could hit each other and make some lithium. And actually, that's all that we could make in the early universe. We didn't get beyond lithium. Okay? But we made a lot of helium-4, a little bit of deuterium, a little bit of helium-3, and a really tiny amount of lithium-7. In fact, for every hydrogen atom in the universe, there were less than 1/1000th of a lithium atom. So if we took a region that had 1 billion atoms in it, one of them might be a lithium atom. Okay? Almost all of them would be hydrogen. Maybe about a tenth of them would be helium, and then a small trace of them would be deuterium, which is just a proton and a neutron, or helium with 2 protons and 1 neutron, called helium-3. Now, the reason we're interested in that, though, is that the exact number of helium atoms that we made and the exact number of deuterium and helium-3 atoms and lithium-7 atoms that were made depend on exactly how many protons and neutrons were flying around in the universe compared to the number of photons. The more protons and neutrons you had, the more efficiently you got everything together to make helium-4. The less you had, the less efficient you were. So that's what this green line shows, is that the more stuff you had, the more protons and neutrons you had, the more helium-4 you made, and the less deuterium and helium-3 you made. And we can go out and measure exactly how much of each of these elements is out there, and that tells us how many protons and neutrons there are for every photon in the universe. Okay? So we can look out there and now realize we're looking back at the universe at the results of a process that ran in the universe, that was happening in the universe when it was anywhere from about a second old to a few minutes old, and we're able to predict exactly how much of these elements should be out there. Okay? And by measuring them, we should be able to tell how many neutrons and protons were in the universe when it was just a few minutes old. And miraculously, what we find is that there's about 1 neutron or proton for every 3 billion photons. Okay? So we were really very, very small trace. Back then, everything was made of light. And there were just a few neutrons and protons hanging around in the universe. There are still about 1 billion photons for every neutron and proton in the universe. Except that the neutrons and protons, they still weigh a lot. They still have a mass of, well, very small mass by our standards. It takes almost 10 to the 24 of them, 1 with 24 zeros to make a gram. But the photons that are running around are the photons of the microwave background. And they're 1 billion times less energetic, actually many billion times less energetic than the protons. So not much of the energy of the universe is in photons anymore, in light. But there are still 3 billion photons for every neutron and proton in the universe. Okay. Well, when we add that all up, that turns out to mean that the density of matter in the universe is a few %. And so if you remember last week when Dr. Gates showed us this census, she told us that by going out and counting the stars and the galaxies and the clusters of galaxies, that the universe had about 5% stuff made in ordinary atoms. And what we found is that that is exactly what studying the abundances of helium and hydrogen and lithium in the universe tell us. So coming from 2 completely different ways of examining the universe, we come to the same result. This is one of the reasons why we have a lot of confidence in our theory. It is able to make predictions. So we predicted 40 years ago that when we went out and looked, we would find that only 5% of the energy of the universe was going to be in atoms. And over the last 20 years, 30 years, we've slowly been accumulating the evidence that, in fact, atoms make up only about 4.5 to 5% of the total energy of the universe. Remember, what are the other parts? Well, about 23% is dark matter. And 72% is this thing called dark energy. Now, what is dark energy? It's exactly like this thing that drove inflation. So dark energy is energy that's out there in empty space without any matter associated with it. Our best guess as to what the dark energy is it just like early in the universe when there was this period where the vacuum, where nothing was the most important source of energy in the universe, and it caused the universe to start expanding faster and faster? The dark energy is exactly the same thing, just much lower energy density. The energy density back then was, well, the energy density in the dark energy today is only the same, equivalent to 10 to the minus 29 grams of matter in a cubic centimeter. That's like 1 proton in about a cubic meter, so in a volume like this. Okay? So very, very little energy, whereas back then it was a much, much larger amount of energy. So somehow the energy of the vacuum is once again coming to dominate the universe. Neither then nor now do we understand exactly how this happened. We have not found the inflaton. We have no good theory that tells us what the inflaton is. Everything that we've tried in our standard model we can show isn't the inflaton. So 2 new mysteries. What is the particle that drove the exponential expansion of the universe when it was far less than a second old, and then decayed to give us all of the matter in the universe? And what is the source of the dark energy today that today makes up 72% of the energy in the universe and is once again starting the universe in this process of an exponential expansion that we can see? So let me go back over the last 3 weeks and review what we've learned. We learned a lot about the size of the universe. We got a sense of the fact that we can't measure the size of a system in the universe in miles or in feet or in kilometers, that we have to use the distance that light travels, the light year, and that even a system as small as our solar system, it takes light a measurable amount of time to cross it. Remember, we learned that it took light 8 minutes to get from the sun to us, and that the nearest stars are several light years away, and that the galaxies that we see with our telescopes are millions to tens of millions to hundreds of millions of light years away. We saw that those very distant galaxies are all moving away from us. And we interpret that as meaning that the universe is expanding. Expanding at the rate where every 10 billion years or so it doubles in size. We found that that rate of expansion, instead of getting slower, like we would expect because of the gravity of all the galaxies pulling on each other, is instead getting faster and faster and faster. And that this meant that those distant galaxies are actually going to recede from view, that we will one day never see them again. And that, in fact, some of the most distant objects in the universe are far enough away that we will never see them as they are today. We will only see them as they were in the past. As the universe expands, we learned that expanding gases cool. And that means that in the past, the universe was much, much hotter. It was full of radiation. That radiation was very hot, much like the inside of the sun. And then as the universe cooled, when it was about 380,000 years old, the protons bound together with the electrons to make neutral hydrogen atoms. And that meant that the light could all of a sudden travel freely through the universe. Exactly like light making its way out through the sun, where it starts off in the center of the sun, and it bounces around for a million years, and eventually it gets out to a place where it's cool enough that there's not much ionized hydrogen. There aren't charged particles running around. Instead, it's all neutral, and so the light can come from there to us directly. In the same way, we are able to look back all the way to when the universe was a few thousand degrees and about 380,000 years old, and probe that entire volume of the universe. Okay. We saw that the universe is full of things that we don't know what they are. That ordinary matter makes up only a few % of the energy of the universe. That dark matter provides over 90% of the gravity of our galaxy and makes up over 20% of the matter of our universe. But that most of the matter, most of the energy, is not either ordinary matter or dark matter, but dark energy. Something that we really have no clue what it is, except perhaps it is just the energy associated with nothing, with empty space. That's our best explanation. And as I've told you today, there was a second form of dark energy back early in the history of the universe, when the universe was fractions of a billionth of a second old. And that dark energy drove a similar rapid and growing and exponential expansion that we term inflation. And that period of inflation was responsible for taking a very small universe, smaller than the head of a pin, that was smooth, but not terribly smooth, nowhere near as smooth as the universe we see, and making it big, smooth, and old. We found that we don't really know the origin of matter, but once we have matter, we know how light elements are made. That matter is really just, even though that matter is just a small piece of the pie. Now, what I didn't tell you is where all the ordinary stuff comes from. Where does carbon come from, and nitrogen and oxygen? They're not made in the early universe. They're actually made in stars. Once we have hydrogen and helium, we're able to we find that we can have that matter that forms into galaxies. It'll start to collapse into little clumps. And those little clumps become stars. Okay? And those stars, inside them, have nuclear furnaces, which slowly burn that hydrogen and that helium into heavier and heavier elements, carbon, nitrogen, oxygen, eventually all the way up to iron. Okay? And then when they explode in supernovas, they make even heavier elements like uranium. Okay? Also, out in interstellar space, we have particles running around and colliding with each other, making some of these elements. So only the first few elements were needed to be made in the early universe, and which is good because we can only make hydrogen, helium, and lithium. So I want you to really take a couple of things away. First is that we understand an awful lot about the universe. And the second is that we don't understand an awful lot about the universe. There are many mysteries that remain. And there's much that we didn't even touch on. We didn't talk about almost any of the objects in the universe, from the planets around the nearby stars to ultra-high energy cosmic rays and everything in between. So stay tuned for future series and future advances. Thank you very much.